Hey, let's talk just a little bit about momentum here. Momentum is a quantity that's really useful when you're talking about things that are colliding together. You can see here the main formula is P equals m times v, the mass times the velocity. Not a whole lot more to say about it than that. There's not even really a good definition of what this quantity represents, except that it's the oomph that the moving object has, and when it hits another object, it's going to transfer some of that momentum to the other object and make it move. So let's see what we've got here. The big deal with momentum is that it is conserved. Okay, there's not a whole lot that we can do. You know, nobody's going to walk up to you in a dark alley and say, "Psst, what's the momentum of this object?" What they're going to want to know is what's the speed of this object if I know the masses and the first velocity or something. So this conservation of momentum is a big deal, and we use that to do a lot of work in collisions, explosions, interactions between two or more objects. We'll just do two. But but that's the thing of it. You remember when we were talking about conservation of energy, that we had a formula that said that E1 equals E2. Well, that's a lot like what we do here. That's conservation. It's the same number before the collision and after the collision. This would be energy, so the same number at top of the hill and the bottom of the hill. We're not so much talking about that as before and after. And we mark this a little bit funny. The before just gets P, P for momentum. Remember that was mass times velocity. But this little tick mark right here, that means after. So here's the before picture and the after picture. You can see that this block is scooting that way, and they're both going to the right, but mass 1 is moving faster. There's a bigger arrow there. It's going to slam into the back of V2, and afterwards they might well be doing something like this because momentum is conserved. You have to have the same amount of total momentum before and after, and that's honestly all that this says right there. Okay? Now, if I have two objects, the mass times the velocity here plus the mass times the velocity here, that total would be equal to the mass times the velocity afterwards. There's that tick mark again, plus the mass of the second object, velocity of the second object afterwards, that. You want to make sure that those two are the same number. So this is what we almost always write when we're talking about momentum being conserved between two objects. Now, clearly, if you came in here with some outside force, then you'd have to adjust for that. But in the event of isolated two objects crashing together, could be a pool ball and another pool ball, could be a bowling ball and a pin, could be two train cars, whatever these are. If they crash together, the momentum has got to be conserved, and you can write this down. And if they give you all of the numbers except for one, you're ready to go. You can solve that thing, and no big deal, right? Just a little bit of algebra there. Here's an example. I've got a bowling ball that's 4 kilograms. It's moving 5 meters per second to the right, and it's going to hit a 2 kilogram stationary bowling pin. All right, pretend that looks like a bowling pin, and it's 2 kilograms. It's stationary, so it's not moving, zero. For convenience, we name one of these object 1 and the other one object 2. So I'd have mass 1, velocity 1. I'd have mass 2 and velocity 2. That's all before the collision. Okay, so that's that before picture. Then we start over again, and it says after the collision. So you can draw a separate picture if you want. Here's that bowling ball. It's still 4 kilograms, so I won't even write that. And the pin is flying off this way somewhere. Okay? That's what we'd like to know. How fast is the pin moving? So I'm going to put V2 prime. Everything in the after picture gets a little tick mark for afterwards. So V2 equals question mark. they do tell me that the ball is moving 3 meters per second to the right. The bowling ball doesn't usually come back and hit you when you go bowling. Right? I'm sorry, that should have been V1 prime. Okay, so mass 1 is the ball, both before and after. It's 4 kilograms both times. It started out moving 5. When it hits the pin, some of its momentum is transferred to the pin, and it loses that momentum, transfers it over. It doesn't lose it, it's still there. But the velocity goes down from 5 to 2. Meanwhile, the pin was not moving. It was stationary, and now it is moving. The total momentum has to be the same. So that's where I come in and I write M1V1 plus M2V2 equals M1V1 prime plus M2V2 prime. Okay? Total momentum before equals total momentum afterwards. As it is, we're looking for this V2 prime, the speed of the bowling pin afterwards. So I need to do a little bit of algebra here, and you can see that if I came along and subtracted M1V1 prime from both sides, then that would be a good start. It would cancel on the right, and I'd have M1V1 plus M2V2 minus M1V1 prime. That's all going to be equal to M2V2 prime. And now, since I want to get that V2 prime by itself, I need to get rid of M2. These being multiplied, I need to divide to cancel. M2 top and bottom. That means I need to divide the left-hand side by M2. And I could put my numbers into that. I'm going to come over here just because of room. But those numbers are on our picture, so we just fill them in. I've got 4 kilograms times 5 meters per second plus M2 times V2. That would be 2 kilograms times 0 meters per second. You can see that's going to cancel out. 2 times 0 is 0. Minus mass 1, the ball was 4 kilograms times its new speed, 3 meters per second. And all of that is divided by mass 2, which was this 2 kilograms right there. That's the number that we're looking for. We get our calculator out. Again, all that addition, subtraction needs to happen before the division, so I'm going to band that up with some parentheses right there, which on the calculator would look like that. I'll have a 4 times 5. I'm going to leave out this middle part because it's just 0. Minus 4 times 3. Close up the numerator, divided by 2, and you get a 4. Okay? The bowling pin wasn't moving at the beginning of the problem, and now it's moving at 4 meters per second. And you can see the ball has gone from 5 to 4. That's where that momentum, that oomph to get the pin moving came from. Some of the ball's oomph got put over on the pin. All right, that's all we're talking about here. Nothing too bad. Now, there's a couple special cases, and this is one of them here. I like to call it the hit and stick formula. The technical name, the fancy name, is the inelastic collision, where these things don't bounce off each other. They don't have their own independent speeds. A good example are 2 train cars. Here I've got mass 1 and mass 2, and they are moving some way. They could be moving towards each other, or like the bowling ball pin, maybe one's sitting still and the other one slams into it. Maybe they're both moving to the right, and the other one hits it from behind. Whatever. But afterwards, they're holding hands right there. They're moving as one unit. It's really, they're stuck together. So that's why I like to call it the hit and stick formula. That might be a little bit of a generalization, but we're going to start with the same idea. The total momentum before is equal to the total momentum afterwards. Right here is that equation that we always write down like that. But we're going to do a little substitution right here. I probably should have put one more step. But V1 prime and V2 prime are the same number. After here, in the after picture, these guys are both going, 5 meters per second to the right. whatever the number is. I made up 5 meters per second, but you know what I'm saying? These two numbers have to be the same. So if we just call it v prime, just kind of forget about the 1 and the 2 for a second, then I could factor that out front, and then I could divide both sides by m1 plus m2, and I would end up with the thing that you see there in the yellow box, where if two things hit and stick, if it's an inelastic collision, I'm always going to have this left side divided by the sum of the masses. That's a special case that comes in pretty handy because lots of things stick together after collisions. And here is an example right here. I've got a truck moving west. It's going to hit a car that's also going west, but at a slower speed. So I'm going to put the car right here. Here comes the truck up behind it. Like that. They're both going to the west, drawn left here, and there's that 2,300 kilogram truck and 11 meters per second. The car was much lighter, 1,200 kilograms. It's only going 7 meters per second. So if you get rear-ended on the highway, this is your problem right here. I hope you don't. But after the collision, the two are stuck together. Maybe the bumper got stuck on the other one. Maybe the truck rode up over and jammed on the hood. Whatever's going on. But there's a pile of junk here where the truck and the car are now stuck together and going down the highway. We would like to know that speed, v prime. So because they're stuck together, I get to use the hit and stick formula, which is v prime equals m1 v1 plus m2 v2 divided by m1 plus m2. Okay? I could go all the way back to that first equation that we talked about right there. Not that one. To this guy in the box, right? But these are the same number. So we make that little substitution. The special case is going to work out a lot better for us right here. All I have to do is put the numbers in. I'd have, you can name either one, car 1 and car 2. Let's just put 1 and 2 like that. I didn't put it down, but I'll put 1,200 times 7. Let me put the units in to be a good boy. All right, 1,200 kilograms times 7 meters per second. And here's 2,300 kilograms at 11 meters per second. And you can see that's my total momentum before the crash. When I divide by the sum of the masses, the 1,200 kilograms and the 2,300 kilograms, then I'll get the total mass. Now I've got addition on top and the bottom, so this would be a capital place to come along and tie the numerator together before that division happens, tie the denominator together like that. So I'm going to do that on my calculator, and it's going to look something like this. I'll have 1,200 times 7 plus 2,300 times 11. There's the top, divided by parenthesis 1,200 plus 2,300. Okay? It's a hit and stick. I get to use the hit and stick formula. Afterwards, they're going 9.63 meters per second. And when we look back at the picture, that kind of makes sense. The truck was moving faster and got slowed down when it hit the car. The car was going 7. It got sped up when the truck hit it. The total momentum is going to be the same. If you wanted to, if it was a rainy afternoon, you didn't have anything else to do, you could say 1,200 times 7 is 8,400. So before this guy has 8,400, and then here's 2,300 times 11, which would be 25,300. You can see how much more momentum the truck has there. But when I put those together, I get a total of 33,700. I've got to have that much at the end. So what we're saying down here is this combined mass would be 1,200 plus 2,300, that's the mass, that would be what, 3,500 kilograms, and now the math tells us it's moving at 9.63. So if I were to multiply those out, I need to get that number right there. I've rounded off a little bit, so it could be that I missed it a little bit, but yeah, I picked up a 5 there somewhere because of my rounding. But that's pretty close, right? That's the idea. It needs to be the same number. Okay. Now, if we've got a special case for hit and stick, I also have a special case for hit and bounce. This would be more like pool balls, right? If I had a ball here that was moving that way, and here's a second ball, maybe it's sitting there, maybe it's moving left, right, whatever, then when those two collide, they're not going to be stuck together. They're not going to be moving at the same speed. They're each going to have their own speed. So I'm going to put them like this, moving towards each other. And afterwards, maybe they bounce off each other and go opposite directions. Something like that. Okay? With these two formulas, the first one would give me the speed of the first ball after the collision, and the second one gives me that different speed of the second ball after the collision. All right? So we can just go through and get that. Now, I'm not going to show you where these come from because it's a pretty big headache. You're solving these two equations simultaneously. This one is a nonlinear equation because of all these squareds. What you're doing here for an elastic collision, you have conservation of momentum, and this one would be conservation of kinetic energy. Okay, that's part of the definition of a perfectly elastic collision, is you don't lose any momentum. Well, you never lose momentum, but you also don't lose kinetic energy. Whereas with the train, you could lose. Where'd that go? This picture right here, let's say that this train was moving left and this one moving right, and they hit and stick. Maybe they both just stop dead in the center, right? They go bonk, and they lose all of that motion. They lose all that kinetic energy. But with an elastic collision, I get to keep all of that kinetic energy. So you just plug these numbers in here. Again, if you've got M1, V1, M2, V2, it's just a matter of plugging in the numbers. I think I've got an example here. Okay, these two, this is the same problem we just had, but now it's a bounce problem. So let me draw it one more time. Car, 1207, and I've got the truck, and it's 2311. They're both moving west like that. So here, because this is a hit and bounce problem, I'd have to use the first formula, V1 prime equals M1 minus M2 over M1 plus M2 V1 plus 2M2 over M1 plus M2 V2, like that. That's the first equation that we had on the thing. Let me just show you one of these. I don't think we need to do them both, but here I would have 1200 minus 2300 over 1200 plus 2300, and then V1, when I put this number in, you know what, I kind of, yeah, we didn't really think about coordinate systems on that other problem, but let's define a coordinate system here. Normally what we do is draw an arrow and call one direction positive and the other direction negative, and we're most comfortable putting the positive to the right. If I do that, then both of these are moving with a negative velocity. The first problem we did where they hit and stuck worked out because they were moving in the same direction. If they're moving in opposite directions, though, they need an opposite sign, so be careful with that. For V1 right here, I'm going to put a -7 representing to the left, west, like that. And then when I do the other one, plus 2 times the second mass divided by the sum of the masses. That's already 3,500, right? Just add these two. And then I've got that negative 11 right there. So that's what I want to do. That's what I want to put in the calculator. You got to be a little bit tricky with this. Some parentheses are in order. Make sure that everything happens just right. Your signs are really important, and they'll trip you up if you're not careful. But up top I'd have 1,200 minus 2,300. I like to go ahead and get that 7 in there before I do the bottom. But down there I had a 3,500. And then I could say plus 2 times 2,300 times negative 11 divided by 3,500. Okay, negative 12.257. 26, how about that? Okay, that would be the speed of the first car after the collision. So you can see that one got bounced pretty hard, right? That truck comes in and hits this guy, bonk, speeds him way up. And we'll go ahead and do the truck too. V2 prime is 2m1 over the sum of the masses times v1 minus m1 minus m2 over m1 plus m2 v2, like that. As long as you get the signs in and can deal with the fractions on your calculator, it's going to be okay. But it's going to look like that times a negative 7. Here's a negative sign. In parentheses, I've got 1,200 minus 2,300, and that's times negative 11, scooting that v up, and dividing by 3,500. So that's what we want to put in there. Nobody said it was fun, but I'll tell you what, these formulas save you a ton of work, because that's a pretty nasty calculation if you don't have the solutions that I gave you. Okay, there's the first part. Now I want to go on and say minus parenthesis 1,200, lost the 1. 1,200 minus 2,300. Close up that parenthesis right there. I've got times negative 11 and divided by the 3,500. It's not hard to do. It's just a little bit tedious. And that's a negative 8.26. Okay, so let's see what those numbers mean again. The car was going to the left with a negative velocity, and now it has an even bigger negative velocity. So this guy shot way out here, and he's going pretty fast because the truck hit him from behind. The truck was going 11, got slowed down to 8, so he lost some speed there. But again, if you go through, the total momentum has got to be the same on both of those. Now, elastic, inelastic, those are kind of funny titles. You do kind of need to remember those. I like to think about if you put on a piece of elastic between two trees and you ran at it, when you hit it, you would bounce, right? Elastic, bounce, inelastic, stick. You're going to stick together. So see if you can keep those together in your head. We're not going to do one of these, but you could have a two-dimensional collision. If you've ever played pool, right, things happen in the X direction and the Y direction, and you'd have to think about those two pool balls moving in 2 dimensions. You could even have 3 dimensions, right? If two people threw a ball and they hit in the air and they're both going, you know, in 3 dimensions, you could have to do this in all 3. But the idea is that you simply conserve momentum in the X direction, and then you conserve momentum in the Y direction. And if you had a 3-dimensional problem, you'd also have the Z direction in there, all right? Like I say, we don't need to worry about doing that, but just be aware that it's another case in physics where if things are happening in multiple dimensions, you take care of each dimension independently and then put it back together. Now, you might remember that we had the work energy theorem. This is the companion to that, called the impulse momentum theorem. And I'm going to put the work energy up here real quick, just for reference. That one said that the work was equal to the change in energy, and most often we wrote that force times distance equals 1/2 mv squared minus 1/2 mv naught squared, right? Okay, so that one is pretty easy to work with because looky right here, they're dealing with force and distance. I've got this other quantity called impulse, which is the force times the time. So that's kind of the tip off here, which way you want to go. If they're talking about force and distance, it's work energy, and if it's force and time, it'd be impulse momentum theorem. And there's a similar thing right here. The impulse is equal to the change in momentum, similar to how the work was equal to the change in energy. All right, but if a problem has time, a collision with time in it, probably an impulse momentum theorem. So that's that. Here's an example. Pitcher throws the baseball. The batter is over here, swings the bat. And we'd like to know how long that bat is actually touching the ball. There's a very small amount of time there that the bat is in contact with the ball. We'd like to find that. So that's a perfect time. Looking at the numbers here, you can see the force is given 130 newtons. They're asking for the time. That's already enough to kind of point us this way. The other variables in there, I've got a 1 kilogram baseball, and the initial velocity is -6 meters per second. Why negative? Because it's going to the left, right? And then after I hit the ball, it's going to be going the other way. So that's a +12. And that's what's happening with those numbers there. But you see how all of those variables are the variables that we have here? Pretty much with a physics problem, if you can get all the numbers, figure out the names of the variables, that pretty well points you to the right formula to use. So nothing too hard here. We are looking for the time. It's right there. All I got to do is get rid of f, and then I'd have time by itself like I want. So if I divide by f on the top cancels f on the bottom. There's time by itself. Got to do it on the other side too. All right, and we're going to put our numbers into that. The time is the mass, 1 kilogram, times the final velocity, 12 meters per second, minus the mass again, 1 kilogram, times the initial velocity, -6 meters per second. And I should have left a little more room. And then I'm dividing by that 130 Newton force, like that. Got some addition, subtraction on top, so let's hold all this together. But that's what we want to do, and it would look like this. I've got parenthesis 1 times 12 minus 1 times a -6. Close up the numerator and divide by 130.138. Okay, now I made up these numbers, so you know this may not be right for baseball, but something like 1/10 of a second. That's not very long. Okay. If anything, I would think this 12 would be a larger number, and that's probably not enough. That's a little bunt, you know, a little short swing. It's not a full-blown. I don't know what a pitcher, how much force he can hit with, but I'm guessing that's a small number there. But still, you can see it's a lot less than a second. For a fraction of a second there, the bat and the ball are in contact, and during that contact, there's a transfer of momentum from the bat to not only stop the ball from going to the left, but to make it go back to the right even faster than it was moving. So here's one thing I'm not going to do a whole lot with, but you know, we've kind of taken the two ends of the spectrum here. Perfectly elastic, I get to keep all the kinetic energy. That's that hit and bounce collision. With the inelastic or hit and stick, I could lose all of the collision. Real life is in between that. Okay, so these two extremes are ideal situations. Might not ever see either one of them really, but train cars are close enough to a hit and stick, and bowling balls and bowling pins are close enough to a hit and bounce. In real life, there is a little bit of lost kinetic energy there, but we say, it's close enough. To deal with that, there's this number called a coefficient of restitution, and you could find that either this way, if you're dealing with two objects that collide, or you could do it this way if it's like the picture that you have here. Something is dropped from a height, and it comes down and it hits the floor, and it bounces up to a new height, h prime, right there. So you could take the height that you dropped it from and the height that it bounced back to, and you can see that you're losing momentum there. You didn't get to keep it all, because it would have bounced right back to the same height that you dropped it from. You're never going to see that in real life, right? You always, drop it from here and it comes back part of the way. Well, that fraction of the height's the square root of the fraction, is a way to measure this coefficient of restitution. What if it was a hit and stick? If I drop some bubble gum, it comes down and it hits the floor and it sticks and it never bounces anywhere. So clearly this is somewhere between, the perfect elastic case would be up here, and it would just keep bouncing to that same height forever. And my perfectly inelastic, where hit and stick is, it's on the floor and it never comes back up off of that. So you don't need to know a whole lot about that, but I just wanted to throw that in there for completeness, and to say that all of these things that we do in physics are models. They're little toys of reality to help us understand reality, but they kind of sweep some factors under the rug. Center of mass is an interesting thing. The momentum works as if all of the mass were concentrated at a single point. So if I took a hammer, I could put my finger right here and balance that hammer on it. The head is heavier than the handle, and so that would be the balance point right there. And that balance point is what the hammer is gonna spin around. You can see that if I draw a line connecting all those center of mass points, that I get that perfectly symmetric curve that we're used to seeing with trajectories, two-dimensional kinematics. But that doesn't really account for the spin of the object. So we kind of mash everything down to a single point when we're thinking about these collisions. We're not thinking about a truck that's 23 feet long and a car that's 12, and there's some rotation of both of them. We just say, they're like point masses. So again, it's a model, and but this is how you would begin to build that in and think about it. We know how to do it. It's just at this level we don't do it, but it's all there. Okay. If you wanted to find the center of mass, you could take, like, say you cut out a piece of plywood or something. You could hang it from one point and let a plumb bob come down across it, and then hang it from some other point. And when the plumb bob comes where those two lines cross, that's the center of mass. And you can put your finger right there and balance that thing. You might have seen mobiles that artists used to do. They were real popular back in the 60s or something. And Calder, for example, did a whole bunch of mobiles and stuff. Where's the center of mass of a donut? Well, it's actually right here, right? It's not even part of the object itself. That's kind of weird. There is a formula. If you have some kind of weird shape and you want to find the center of mass, you can, in your head, cut it into little pieces, find the center of mass of each one, and then there's a formula that you can do to find how far left or right that center point is, and how far in the y direction, how far up and down it is from using all that. You don't need that, okay? Just put it in for kicks. So that's that's what I've got for you today. The things that I'm most interested in you remembering would be, and I don't know why there's not a summary at the end of this, but right there, the momentum is mass times velocity. So that's one you should keep up with. If it's conservation of momentum, you've got this. There are two special cases where you have the hit and stick formula, and these two, the hit and bounce formula. And then the impulse momentum theorem would be nice to have on your card as well. Okay, those are the kinds of problems that we're interested in. They're almost all collision problems of one kind or another. All right. So thanks for stopping by. Don't worry about any of the center of mass stuff or the coefficient of restitution, and it will be all right. Thanks for everything. Have a great day.